Earlier, we gave you all of these tools to help you approximate definite integrals. We talked about trapezoidal sums, and we talked about all sorts of Riemann sums, whether that be upper, lower, right, left Riemann sums, all of those. And what I want to do in this video is give you another tool to help you approximate definite integrals. And that tool is called Simpson's rule. Simpson's rule. Simpson's rule. And Simpson's rule, I want to apply that to this example here to give you some feel for what it's saying and how it works and what it looks like. Simpson's rule needs to have an even number of subintervals to use it. So in this example up here, we're going to chop this up into 4 even subintervals. But that's to say that Simpson's rule n, so the number of subintervals that we have, needs to be an even number. So n needs to be even. And if we were to apply Simpson's rule to this example, let's see what it's doing. So Simpson's rule, let's throw some notation down. So we have x naught, we'll say that this is x sub 1, x sub 2, x sub 3, and x sub 4. Okay, and Simpson's rule, again, is going to do this. So rather than constructing all of these rectangles here or trapezoids, Simpson's rule is going to construct some quadratic functions. And in this case, it's going to make a bunch of parabolas. So these 3 points here, these 3 points are going to be used to construct a parabola. So if we were to draw out maybe what a parabola would look like between these 3 points, it's something like that. And then all we're going to do is find the area. Find the area under this parabola here in these 2 subintervals. So we take the area under this parabola. And then similarly, for our remaining 2 subintervals, we're going to construct another parabola. The Simpson's rule is going to construct another parabola. And then it's going to find the area under this as well. So maybe this parabola would look something like that. And then we would find the area under it. So we'd get the area under it, like that. So that's what Simpson's rule is doing. And then if we were to write out, how would we calculate that? Well, we would write this. So we're going to take Simpson's rule with how many subintervals? Well, we're going to have 4 here, we said. So these are all delta x. Okay, delta x. And this is going to be Simpson's rule with 4 subintervals. And it's equal to a delta x. Let's get that in pink. It's equal to a delta x. I want pink. There we go. Delta x over 3. And similar to how we computed all these other sums, we're going to define delta x as the same thing. It's going to be the length of our interval. So x sub 4 minus x naught. And then over how many subintervals we have. And that's going to be 4. So that's delta x. It's not something new. But anyways, Simpson's rule. It is saying we're taking delta x divided by 3, and then we're multiplying that by this entire thing here. So f of x naught, and then plus 4 times f of x sub 1, plus 2 times f of x sub 2, and then plus 4 times f of x sub 3, and then finally plus f of x sub 4. So this is Simpson's rule applied to this example up here. And just a few things to note. This isn't stated in general. So if we had a larger number of subintervals here, you would see that this pattern of alternating between 4s and 2s would continue on. You would see that. And then also, you might be wondering, where are these 4s and 2s and 3 coming from? And don't worry, we'll do a derivation on Simpson's rule, and you'll feel much better. You'll get some more intuition on where these come from, how we get Simpson's rule. So that will be in a few videos. I just wanted to introduce it to you and tell you that it's this super powerful tool, and you'll see just how accurate it is in the upcoming videos. And in the next video, we're going to apply Simpson's rule to an example.